Right now, in the space between your hand and whatever surface is closest to it, something is happening. Not atoms drifting, not dust floating, something far stranger. The quantum fields that fill every cubic centimetre of the universe, including the emptiest void you can imagine, are refusing to sit still. They cannot be silent. They cannot be zero. Physics itself forbids it. What we call empty space is not empty at all. It is a restless, humming, physically real state of underlying fields that never fully quiet down, even when every particle has been removed, even when nothing visible remains. And the reason they can never be still strikes at one of the deepest truths about how reality is actually built. Tonight, we are going to understand why the universe, at its most fundamental level, is incapable of true silence. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you were probably taught in school. You were told that the world is made of atoms, that atoms are made of smaller pieces, protons, neutrons, electrons. Maybe you learned that protons and neutrons are made of even smaller things called quarks. And at some point, the picture in your head settled into something like this. The universe is built from tiny objects, little solid specks of stuff, flying around, bouncing off each other, clumping together to make everything you see. Rocks, water, stars, you. That picture is not exactly wrong, but it is deeply incomplete. And the incompleteness matters enormously for what we are about to explore tonight. Because the moment you replace that picture with the one modern physics actually uses, something very strange follows. Something that changes what you think empty space is, what you think nothing means, and what you think is happening in every single point of the universe right now, including the space inside your own body. So let's rebuild the picture from scratch. Not with speculation, not with metaphor, with what physicists have actually discovered over the last century through some of the most precise experiments ever conducted. The idea that matter is made of tiny, indivisible particles goes back thousands of years. Democritus, a Greek philosopher working around 400 BC, proposed that if you kept cutting a piece of material in half, eventually you would reach something that could not be cut any further. He called these smallest pieces atoms, from the Greek word meaning uncuttable. It was a brilliant guess, but for over 2,000 years it remained just that, a guess. There was no way to test it, no way to see atoms, no way to prove they existed. That changed in the 1800s. Chemists noticed that elements always combined in fixed ratios by mass. Hydrogen and oxygen always made water in the same proportions. Carbon and oxygen always made carbon dioxide the same way. This made perfect sense if matter came in discrete units with definite masses. If a water molecule was always 2 hydrogen atoms and 1 oxygen atom, the ratios would always be the same. The evidence was indirect but compelling. Then, in 1905, Albert Einstein published a paper explaining Brownian motion, the random, jittery movement of tiny particles suspended in fluid. He showed that this motion was caused by invisible atoms and molecules constantly bombarding the particles from all sides. His equations let scientists calculate the size and mass of individual atoms. Atoms were real. They had definite sizes, roughly 1/10,000,000th of a meter across. You could line up about 10 billion of them across a single meter. But almost immediately, atoms turned out not to be fundamental. In 1897, J.J. Thomson discovered the electron, a tiny negatively charged particle that could be pulled out of atoms. Atoms were not indivisible after all. They had internal parts. Then in 1911, Ernest Rutherford fired fast-moving particles at thin gold foil and found that most passed straight through, but a few bounced back at sharp angles. This could only happen if each atom had a dense, positively charged core, the nucleus, surrounded by mostly empty space, where electrons orbited at relatively large distances. The atom was not a solid ball. It was almost entirely empty, with a tiny, dense centre and lightweight electrons far away. The nucleus itself was found to contain protons, carrying positive charge, and neutrons carrying no charge. And then in the 1960s and 70s, experiments at particle accelerators revealed that protons and neutrons were not fundamental either. Each proton is made of 2 up quarks and 1 down quark. Each neutron is made of 1 up quark and 2 down quarks. Quarks are held together by particles called gluons, which carry the strong nuclear force. So by the late 20th century, the picture looked like this. Matter is made of atoms. Atoms are made of electrons orbiting nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. Quarks and electrons, as far as we can tell, have no further internal structure. They appear to be fundamental. The world is built from a collection of fundamental particles. This is where most science education stops, and it leaves you with a picture that is clean and intuitive. Reality is made of tiny objects. Find the smallest objects, understand how they interact, and you understand everything. But here is the problem. That picture does not actually match how modern physics works. It is not how the most successful theory in the history of science, quantum field theory, actually describes the universe. And the difference is not a minor technical detail. It is a complete change in what you consider the fundamental stuff of reality. In quantum field theory, particles are not the fundamental entities. Fields are. Let me explain what that means, because the word field gets used loosely, and if you do not understand it precisely, everything that follows will seem vague or mystical. It is neither. A field, in physics, is something that has a value at every point in space. That is the core idea. Not a complicated idea, not a mysterious idea, just something that assigns a number, or a set of numbers, to every location. Think about temperature in a room. At every point in the room, there is a temperature. Near the window it might be cooler. Near the heater it might be warmer. The temperature varies smoothly from place to place. If you could measure the temperature at every single point simultaneously, you would have a temperature field. It fills the entire room. It does not exist at just one location. It is everywhere, with a value at each point. Or think about the surface of a calm lake. At every point on the surface, the water has a certain height. If the lake is perfectly still, every point is at the same height. If you drop a stone in, ripples spread out. The height at each point changes over time, rising and falling as waves pass through. The surface height is a field defined over the two-dimensional surface of the lake, and the waves, the ripples, are disturbances in that field. They are not separate objects sitting on the water. They are the water itself, displaced from its resting state, propagating across the surface. This is the key analogy. Hold on to it. In quantum field theory, every type of fundamental particle corresponds to a field that fills all of space. There is an electron field. There is a quark field, actually several quark fields, one for each type of quark. There is an electromagnetic field. There is a field for every fundamental particle we have discovered. These fields are not confined to specific locations. They are not sitting inside atoms or hiding inside particle accelerators. They permeate all of space. Every cubic centimetre of the universe, whether it contains visible matter or not, is filled with these fields. They are everywhere, always, extending in all directions without boundary. And here is the crucial part. What we call a particle is not a tiny object. It is a localized excitation of one of these fields. An electron is not a little ball orbiting a nucleus. It is a ripple, a specific kind of disturbance in the electron field. A photon is not a little pellet of light flying through space. It is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Go back to the lake. When a wave passes across the surface, you might point at the crest and say there is a wave right there. But the wave is not a separate thing sitting on the water. It is the water, temporarily displaced, carrying energy across the surface. The wave is an excitation of the lake's surface. It belongs to the lake. Without the lake, there is no wave. Particles work the same way. An electron is an excitation of the electron field. Without the electron field, there is no electron. The field is the fundamental thing. The particle is what you get when the field is disturbed in a particular way. This is not a metaphor. This is not a teaching simplification. This is the actual content of quantum field theory, the framework that underlies all of modern particle physics. When physicists at the Large Hadron Collider smash protons together at nearly the speed of light and observe what comes out, they are not watching tiny balls break apart and reassemble. They are dumping energy into quantum fields and watching those fields respond by producing new excitations, new particles, according to precise mathematical rules. This might seem like an abstract distinction. Who cares whether we call the electron a particle or a field excitation? But the distinction matters enormously because fields and particles behave very differently in one critical respect. Particles can be absent, fields cannot. If you think of the universe as being built from particles, then a region of space with no particles in it is simply empty. There is nothing there. The container is vacant. End of story. But if you think of the universe as being built from fields, the situation changes completely. You can remove every particle from a region of space. You can extract every photon, every electron, every quark, but you cannot remove the fields. The electron field does not vanish just because there are no electrons present. The electromagnetic field does not disappear just because there are no photons flying through. The fields remain. They are always there. Think about the lake again. You can wait for every wave to die down. Every ripple, every disturbance can fade away until the surface is perfectly calm. But the lake is still there. The water has not disappeared. The surface still exists, sitting at every point, quiet but present. You have removed all the excitations, all the waves, but you have not removed the thing that was waving. This is what happens when you remove all particles from a region of space. You remove all the excitations. Every electron, every photon, every quark, everything detectable. But the fields remain. The electron field is still there. The electromagnetic field is still there. Every quantum field that permeates the universe is still there, filling that region, present at every point. You have not created nothingness. You have created the quietest possible state of the fields. Physicists call this the vacuum state. It is the ground state, the lowest energy configuration that the fields can achieve. And this distinction between a region with no particles and a region with no fields is everything. It is the entire foundation of what we are exploring tonight. Because the vacuum state, this quietest possible configuration of all the quantum fields, turns out not to be quiet at all. Not in the way you might expect. But before we get there, let me make sure the field picture is solid in your mind, because it is easy to slide back into thinking about particles as little objects, and if you do, the rest of this will not make sense. Consider the electromagnetic field. This is probably the most familiar quantum field, because its excitations are photons, particles of light. The electromagnetic field fills all of space. It is present in every room, every vacuum chamber, every region of intergalactic space. When you turn on a light, you are creating excitations in the electromagnetic field. Photons are being produced, ripples in the field that carry energy from the light bulb to your eye. When you turn off the light, the photons that were illuminating the room get absorbed by walls, furniture, your body. The excitations dissipate. But the electromagnetic field itself does not go away. It is still there, filling the room, sitting in its lowest energy state. No photons are present, but the field is very much present. The same is true for the electron field. Right now, there are electrons all around you. They are part of every atom in your body, in the air, in everything you can see and touch. Each one is an excitation of the electron field. But the electron field extends far beyond the locations of those electrons. It fills the spaces between atoms. It fills the spaces between molecules. It extends into the vacuum of outer space, into the voids between galaxies, everywhere. Even in regions where no electron has ever been, and perhaps no electron will ever be, the electron field is there. This is worth sitting with for a moment, because it runs completely counter to everyday intuition. We experience the world as being made of objects, solid things in definite places, tables, chairs, stars, people. And between the objects, there seems to be nothing, just space, just emptiness. But according to quantum field theory, that space is not empty. It is saturated with fields. The electromagnetic field, the electron field, the muon field, the quark fields, the neutrino fields, the Higgs field, and several others. All of them overlapping, all of them coexisting, all of them filling every point in space simultaneously. This is not speculation. The existence of these fields has been confirmed through experiments spanning decades. The predictions of quantum field theory have been tested to extraordinary precision. The magnetic moment of the electron, a quantity that depends on the detailed behavior of the electron field and the electromagnetic field interacting with each other, has been calculated in quantum field theory and measured experimentally. The agreement between theory and experiment is extraordinary, one of the most precise matches between prediction and measurement in the entire history of science. The fields are real. Their behavior is understood with astonishing accuracy, and they are everywhere. Now, here is something important to clarify about what the word field means in this context, because it is easy to imagine something wispy or ghostly, like a fog filling a room. That is not quite right. A quantum field is not a substance in the ordinary sense. It is not made of anything more basic. It does not have a texture or a color or a density the way fog does. A quantum field is a physical entity defined by its mathematical properties, specifically by how its values at different points in space change over time and interact with other fields. It is as real as anything else in physics, but it is a different kind of thing than the objects you encounter in daily life. When physicists say a field has a value at every point, they mean something precise. At each point in space, the field has a certain amplitude, a certain strength. For some fields, this value is a single number at each point. For others, it involves multiple numbers encoding direction as well as magnitude. The electromagnetic field, for example, has 6 components at each point, 3 for the electric part and 3 for the magnetic part. These values change over time as the field evolves. When the values change in a coordinated way, oscillating up and down in a pattern that moves through space, that moving pattern is what we detect as a photon, a particle of light. The Higgs field deserves special mention here because it illustrates something important about fields and particles. The Higgs field is a quantum field that, unlike most others, has a non-zero value even in its vacuum state. Most fields, in their lowest energy configuration, have an average value of 0. The electromagnetic field in its ground state has no net electric or magnetic field. But the Higgs field is different. Its lowest energy state corresponds to a non-zero value throughout all of space. This non-zero background value is what gives mass to fundamental particles like quarks and electrons. They acquire mass by interacting with this ever-present Higgs field as they move through space. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was a landmark moment in physics. But what was actually discovered was not a tiny ball. It was evidence that the Higgs field exists, that it fills all of space, and that it can be excited to produce a characteristic ripple, the Higgs boson, when enough energy is concentrated in a small enough region. The particle confirmed the field, not the other way around. This reversal of priority, fields first, particles second, is one of the most important conceptual shifts in 20th century physics. And it was not obvious. It took decades of theoretical development and experimental confirmation to establish. The roots go back to the late 1920s, when Paul Dirac combined quantum mechanics with special relativity and produced the Dirac equation, which described the electron in a way consistent with Einstein's theory. But the Dirac equation also predicted something bizarre. It predicted the existence of antimatter, specifically the positron, a particle with the same mass as the electron, but opposite charge. The positron was discovered experimentally in 1932 by Carl Anderson, confirming Dirac's prediction. But the deeper lesson was not just that antimatter exists, it was that particles could be created and destroyed. In classical physics, matter is conserved. You cannot create or destroy atoms, they just rearrange. But in quantum field theory, particles are excitations of fields, and excitations can appear and disappear. If you put enough energy into the electron field, you can create an electron-positron pair, a particle and its antiparticle. If an electron and a positron meet, they annihilate, their energy transferring into excitations of the electromagnetic field, meaning photons. Particles are not permanent objects. They are temporary patterns in underlying fields. This has been confirmed in countless experiments. Particle accelerators routinely create particles that did not exist before the collision. Energy goes in, new excitations come out. The total energy is conserved, but the number and types of particles change. This only makes sense if the fundamental entities are the fields, not the particles. The fields are permanent, the particles are temporary. Throughout the 1940s and 50s, physicists developed quantum electrodynamics, the quantum field theory of the electromagnetic field and the electron field. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga each independently developed methods to calculate how these fields interact, and their methods gave identical predictions. The theory was enormously successful, matching experiment after experiment with extraordinary precision. It was the prototype for all subsequent quantum field theories. In the 1960s and 70s, physicists extended the approach to the other fundamental forces. Sheldon Glashow, Abdus Salam, and Steven Weinberg unified the electromagnetic force with the weak nuclear force into a single electroweak theory. Quantum chromodynamics was developed to describe the strong nuclear force binding quarks together inside protons and neutrons. Together, these quantum field theories form what is called the standard model of particle physics. It describes three of the four known fundamental forces: electromagnetism, the weak force, and the strong force, and all known fundamental particles as excitations of underlying quantum fields. The standard model has been tested in thousands of experiments over more than 50 years. Its predictions have been confirmed time and again. It successfully predicted the existence of particles before they were discovered, including the W and Z bosons found at CERN in 1983, the top quark found at Fermilab in 1995, and the Higgs boson found at CERN in 2012. It is, by any reasonable standard, the most successful scientific theory ever constructed. And its message is clear. The universe is not built from particles, it is built from fields. Particles are what fields do when they are excited. So let us take stock of where we are. Every point in space, right now, is filled with quantum fields. The electromagnetic field, the electron field, the muon field, the tau field, the up quark field, the down quark field, the charm quark field, the strange quark field, the top quark field, the bottom quark field, the electron neutrino field, the muon neutrino field, the tau neutrino field, the gluon fields, the W and Z boson fields, and the Higgs field. They are all here, right now, at every location, overlapping and coexisting. Most of them, in the space around you, are in their ground state. They are not producing detectable particles. They are quiet. But what does quiet mean for a quantum field? That is the question. Because in classical physics, quiet would mean still, perfectly calm, no disturbance, no motion, no energy. Like a perfectly flat lake with no waves at all, zero activity, absolute stillness. But quantum fields are not classical. They obey the laws of quantum mechanics. And quantum mechanics has something very specific to say about whether a field, or anything else, can truly be perfectly still. The answer, as we are about to discover, is no. Not approximately no, not usually no. Absolutely, fundamentally, built into the laws of physics, no. The fields filling every point of space cannot be perfectly still. Their quietest possible state, the vacuum, is not a state of zero activity. It is a state of minimum activity. And minimum, in quantum mechanics, is never zero. This is the heart of what it means that quantum fields never stay quiet. Not because something is shaking them from outside, not because stray particles are wandering through, but because the internal logic of quantum mechanics forbids perfect stillness. The fields, even at their calmest, must retain a residual hum of activity that can never be removed. And that hum, that irreducible restlessness, turns out to have measurable physical consequences that reshape our entire understanding of what empty space actually is. To understand why, we need to look carefully at what happens when you try to force a quantum system into absolute stillness. We need to understand what the vacuum state really is and why it is not what you think. And we need to confront a principle at the heart of quantum mechanics that makes true silence not just unlikely, but impossible. So now you understand the foundation. The universe is not built from tiny solid objects. It is built from fields. Quantum fields that stretch across all of space, filling every point, present everywhere simultaneously. What we call particles are just localized excitations of those fields, temporary ripples in something far more fundamental. And those fields do not disappear when the particles do. Remove every detectable particle from a region of space, and the fields remain. Silent, perhaps, but very much present. This raises a question that sounds simple, but turns out to be one of the most important questions in all of physics. What is empty space? Not empty in the casual sense of a room with no furniture. Empty in the most extreme sense you can imagine. Take a region of space. Remove every atom. Remove every molecule. Remove every photon of light, every neutrino passing through, every particle of any kind. Cool it down to absolute zero so there is no thermal radiation. Shield it from every external influence you can think of. Pump out everything until there is nothing left that any instrument could detect. What remains? If your picture of reality is based on particles, the answer seems obvious. Nothing remains. You removed everything. The space is empty. It is void. It is a blank container with nothing inside. Just coordinates, just volume, just geometric emptiness with no physical content at all. But if your picture of reality is based on fields, the answer is completely different. Because you cannot remove the fields. You cannot pump out the electron field the way you pump out air molecules. You cannot extract the electromagnetic field from a region of space the way you can extract photons from it. The fields are not things inside space. They are part of what space is. They are the physical fabric that fills all of space and gives it physical content. When you remove all the particles, all you have done is remove all the excitations. The fields themselves remain, sitting in their lowest energy state, quiet but present, filling every point of that supposedly empty region. This is the vacuum state. And understanding what it actually is, understanding why it is not nothing, understanding why it is a physically real state with real physical properties, is essential to understanding why quantum fields never stay quiet. Let me build this up carefully, because the difference between the vacuum and true nothingness is subtle but profound. Start with a thought experiment. Imagine you have a sealed box, a perfectly sealed, perfectly insulated box that nothing can get into or out of. Now, imagine you could somehow remove everything from inside that box. Every gas molecule, every dust particle, every stray photon, everything. You pump and pump and pump until there is absolutely nothing detectable left inside. In the 17th century, this question fascinated natural philosophers. Could a true vacuum exist? Could you have a region of space with literally nothing in it? Aristotle had argued that nature abhors a vacuum, that empty space was impossible because something would always rush in to fill it. This was not a scientific argument in the modern sense, it was philosophical. But it influenced thinking for nearly 2,000 years. Then in 1643, Evangelista Torricelli performed a famous experiment. He filled a glass tube with mercury, sealed one end, and inverted it in a dish of mercury. The mercury in the tube dropped, leaving a space at the top. No air could have gotten in. The space above the mercury appeared to be empty. Torricelli had created the first artificial vacuum, or at least something very close to one. A few years later, in 1654, Otto von Guericke performed his famous Magdeburg hemispheres experiment. He placed two large copper hemispheres together and pumped the air out from between them. The resulting vacuum held the hemispheres together so tightly that two teams of horses pulling in opposite directions could not separate them. The atmospheric pressure on the outside, with nothing pushing back from inside, created an enormous force. The demonstrations were spectacular and convinced many people that vacuums were real, that you could indeed remove the air from a region and leave nothing behind. But here is the key question that nobody in the 17th century could have answered. When Torricelli or von Guericke removed the air, did they create true emptiness? Was the space they created genuinely empty, genuinely void, genuinely containing nothing at all? The answer is no, not even close. Even the best vacuum they could create was filled with things they could not detect. Thermal radiation, for one. Every surface emits electromagnetic radiation based on its temperature. The walls of their vessels were radiating photons into the vacuum space. They had no way to detect these photons, no concept of electromagnetic radiation as we understand it today, but the radiation was there. Modern vacuum technology has gone enormously further. The best laboratory vacuums today can reduce the gas pressure inside a chamber to less than 1/1,000,000th of atmospheric pressure. In such a chamber, the average distance between remaining gas molecules is larger than the chamber itself. For most practical purposes, the gas is gone. The International Space Station orbits in a region where the gas density is roughly 100 billion times lower than at sea level. And in the depths of intergalactic space, far from any galaxy, the density drops to approximately 1 atom per cubic meter. These are extraordinarily empty environments by any human standard. But even in deep intergalactic space, the space is not truly empty. It is filled with the cosmic microwave background radiation, photons left over from about 380,000 years after the Big Bang, cooled by the expansion of the universe to a temperature of about 2.7 Kelvin, just above absolute zero. Every cubic centimeter of space, everywhere in the observable universe, contains roughly 400 of these ancient photons. You cannot see them with your eyes. They are microwave photons, with wavelengths of about a millimeter. But they are there, filling all of space with a faint glow of ancient light. And there are neutrinos. The cosmic neutrino background, produced in the first seconds after the Big Bang, fills all of space with roughly 336 neutrinos per cubic centimeter. These are ghostly particles that barely interact with anything. Trillions of them pass through your body every second without touching a single atom. But they are there, everywhere, in every region of space. So the space between galaxies, as empty as anything we know of in the physical universe, is still filled with photons and neutrinos and the occasional hydrogen atom. It is not truly empty by any strict definition. But let us go further. Let us do something we cannot actually do in practice, but can imagine in principle. Let us somehow remove all of those things too. Remove every cosmic background photon. Remove every neutrino. Remove every last atom of hydrogen drifting through the void. Remove every particle of every kind, every form of radiation, every detectable entity. Leave nothing behind. What is left? In classical physics, the answer would be geometric space, a container with no contents, coordinates in 3 dimensions, volume and distance and direction, but nothing physical filling the space. Just the stage, with no actors and no props. A true void. Absolute nothingness. This is the classical concept of the vacuum, and it has an ancient pedigree. It goes back to the atomists of ancient Greece, who imagined atoms moving through an infinite void. It was the picture most physicists held until the 20th century. Space is a passive backdrop. Matter and energy are the actors. Remove the actors, and only the empty stage remains. But quantum field theory says something radically different. When you remove every particle, every excitation, every detectable entity, you do not get nothingness. You get the vacuum state of every quantum field. And the vacuum state is not nothing. It is a specific physical state with definite physical properties. Let me explain what this means with real precision, because it is one of the most commonly misunderstood ideas in all of physics. Every quantum field has a spectrum of possible states. Think of it like a musical instrument with many possible notes. You can excite the field in various ways, producing different particles with different energies and momenta. A photon with a certain energy is one excitation of the electromagnetic field. A photon with a different energy is a different excitation. An electron moving in one direction is one excitation of the electron field. An electron moving in another direction is a different excitation. The field can support an enormous variety of excitations, each corresponding to a specific particle or combination of particles. But there is always a lowest state, the state with the least energy. The state you get when you have removed every excitation you possibly can, when the field is as quiet as it is capable of being. This is the vacuum state, the ground state, the lowest rung on the ladder. It is the quantum field equivalent of a perfectly still lake with no waves at all. Except that analogy is about to break down, because a quantum field in its vacuum state is not actually still. We will get to why in detail shortly. For now, the important point is this: the vacuum state is a state. It is not the absence of a state. It is not nothingness. It is a specific, well-defined physical configuration of the field with specific, well-defined physical properties. This distinction matters enormously. Nothingness, true nothingness, would mean no fields at all. No electromagnetic field, no electron field, no space, no time, no physical content of any kind. That is not what you get when you empty a region of space. You get the vacuum state. The fields are still there. They are in their lowest energy configuration, but they have not vanished. Here is an analogy that might help, though like all analogies, it is imperfect. Think about the concept of 0 degrees on a thermometer. When the temperature in a room drops to 0 degrees Celsius, the room is not empty of temperature. 0 is a temperature. It is a specific physical state of the air molecules in the room, corresponding to a specific average kinetic energy. It is cold, certainly, but it is not the absence of thermal properties. The air still has thermal properties. It still has a temperature. That temperature just happens to be at a particular reference point we label 0. The vacuum state is something like this. It is the 0 point of the quantum fields. Not the absence of the fields, but the fields at their lowest possible level. The fields still exist. They still have physical properties. Those properties just happen to correspond to the quietest configuration the fields can achieve. Now, someone might object. This is just semantics. Who cares whether we call it nothing or the vacuum state? What practical difference does it make? The difference is enormous, because nothingness by definition has no properties. True nothingness cannot push or pull on anything. It cannot exert forces. It cannot store energy. It cannot affect the behavior of particles passing nearby. It is the absence of everything, and so it does nothing. But the vacuum state does have properties. Measurable, physical, experimentally confirmed properties. The vacuum state can exert forces on physical objects. It can affect how particles behave. It contributes to the energy of atoms. It can be changed, deformed, and disturbed by external conditions, like the presence of matter or the curvature of space-time. It is a physically active state, not a passive absence. We will explore the specific experimental evidence for this when we discuss the Casimir effect and the Lamb shift later. But for now, simply register the point. The vacuum is not nothing, it is something. Something real, something physical, something measurable. And this fact changes everything about how we understand what empty space actually is. The classical picture of the void, the idea that empty space is a featureless, inert backdrop against which the drama of physics plays out, is wrong. Space is not a container, or rather, it is not merely a container. It is filled, saturated, permeated by quantum fields. And even when those fields are in their quietest possible state, they have physical content. They can do things. They affect the world. This realization did not come all at once. It developed gradually through the 20th century as quantum mechanics and quantum field theory matured. One of the earliest hints came from Max Planck himself, the physicist who started the quantum revolution. In 1911 and 1912, Planck was working on the theory of thermal radiation, the light emitted by hot objects. He derived a formula for the energy of oscillating systems at different temperatures, and his formula had an interesting feature. Even at absolute zero, the lowest possible temperature, the oscillators in his model still had a residual energy. They did not stop moving. They retained a minimum, irreducible amount of energy that could not be extracted. Planck noted this, but did not make much of it at the time. A few years later, in 1913, Planck and Einstein discussed this residual energy and its implications. Einstein had been thinking about similar problems. He and Otto Stern published a paper in 1913 examining the thermodynamic consequences of this zero-point energy, as it came to be called. They found that the existence of zero-point energy had measurable effects on the specific heats of materials at low temperatures. It was not just a mathematical curiosity, it was a physical reality. When quantum mechanics was formally developed in the 1920s by Werner Heisenberg, Erwin Schrödinger, Max Born and others, zero-point energy emerged naturally from the theory. Consider the simplest quantum mechanical system, the harmonic oscillator. This is a system that oscillates back and forth around an equilibrium point, like a ball on a spring. In classical physics, the ball can sit perfectly still at the equilibrium point, with zero energy of motion. It does not have to oscillate, it can simply rest. But in quantum mechanics, the harmonic oscillator cannot have zero energy. Its lowest energy state, the ground state, has an energy of 1/2 times Planck's constant times the oscillation frequency. This is the zero-point energy. It is always there, always non-zero, no matter how cold you make the system, no matter how much energy you extract. You cannot go below the ground state. You cannot reach zero energy. The system always retains this irreducible minimum. This is not because we lack the technology to cool things further. It is not a practical limitation. It is a fundamental consequence of the Heisenberg uncertainty principle, which we will examine in detail in the next section. The uncertainty principle forbids the oscillator from being perfectly still, and that prohibition translates directly into a minimum energy that can never be removed. Now extend this reasoning from a single oscillator to a quantum field. A quantum field filling all of space can be mathematically decomposed into an infinite collection of independent oscillators, one for each possible wavelength and direction of vibration. Each of these oscillators has its own ground state with its own zero-point energy. The vacuum state of the field is the state in which every single one of these oscillators is in its ground state. No excitations, no particles, everything at the absolute minimum. But every oscillator still has its zero-point energy, and there are infinitely many oscillators. This creates a puzzle we will return to later, because the total zero-point energy of all these oscillators, summed up, gives an answer that is either enormous or infinite, depending on how you do the calculation. This is one of the deepest unresolved problems in physics, but the key point for now is simpler. Even in the vacuum state, the fields carry energy. They are not at zero. They are at a minimum, but that minimum is not zero. This means the vacuum is not energetically inert. It has energy. It has physical content. It is doing something, even when no particles are present. The fields are in their lowest state, their quietest configuration, but that configuration is not silence. It is a hum so low and so pervasive that you cannot remove it, a fundamental baseline of activity that persists no matter what you do. Let me emphasize something here that often gets lost in popular discussions of this topic. When physicists say the vacuum has energy, they do not mean there are particles hiding in it. They do not mean electrons and photons are secretly lurking below the threshold of detection. The vacuum state is not a state with hidden particles. It is a state with no particles. Zero photons, zero electrons, zero everything. It is the state in which the answer to the question of how many particles are here is definitely zero. And yet the fields are not at rest. Their values are not fixed numbers. They fluctuate. The energy is not zero. These are not contradictory statements. A field can have no particles and still not be at rest. The vacuum is a state of no excitations, but non-zero activity. This is precisely what makes it so strange and so important. This distinction, the distinction between no particles and no activity, is where popular explanations of quantum physics most often go wrong. You may have heard that empty space is full of particles popping in and out of existence, that virtual particles are constantly appearing and disappearing, borrowing energy from the vacuum and giving it back. This language is so widespread that it has become almost standard in science communication. But it is misleading, deeply misleading. We will address this carefully shortly, because understanding what is actually happening in the vacuum, as opposed to what the pop science version says is happening, is crucial to understanding why quantum fields never stay quiet. The real story is subtler and more interesting than particles popping in and out. For now, let me build one more layer of understanding about the vacuum by talking about what happens when you change the conditions around it. If the vacuum were truly nothing, it would not respond to anything. You cannot interact with nothingness. You cannot push on it, pull on it, deform it, or change it. But the quantum vacuum responds to external conditions. It changes its properties depending on the physical situation. Consider what happens when you place two uncharged metal plates very close together in a vacuum. There is nothing between them. No electric charge, no magnetic field source, no particles of any kind. Classically, there should be no force between them. They are neutral, separated by empty space, and there is nothing to create an attraction or repulsion. But experimentally, there is a force. The plates attract each other. This is the Casimir effect, first predicted by Hendrik Casimir in 1948 and measured with increasing precision over the decades since. The force is tiny, but it is real and measurable. We will discuss the details of this effect later. What matters now is what it tells us about the vacuum. The Casimir effect exists because the vacuum between the plates is different from the vacuum outside the plates. The presence of the plates changes the boundary conditions for the quantum fields. Between the plates, only certain wavelengths of field oscillation can fit. It is similar to how only certain wavelengths can exist on a guitar string that is fixed at both ends. The string cannot vibrate at just any frequency. It can only vibrate at frequencies whose wavelengths fit evenly between the fixed endpoints. These are the harmonics. Similarly, the electromagnetic field between two metal plates can only support oscillations whose wavelengths fit between the plates. Longer wavelengths are excluded. This means the vacuum between the plates has fewer oscillation modes than the vacuum outside the plates. Each mode carries 0 point energy, so fewer modes means less vacuum energy between the plates than outside. This energy difference creates a net force pushing the plates together. This is remarkable. The force does not come from any particle. It does not come from any radiation. It comes from the difference in vacuum energy between two regions of space with different boundary conditions. The vacuum itself, the state with no particles, is exerting a measurable physical force. Try explaining that if you think the vacuum is nothing. The Lamb shift is another example. In 1947, Willis Lamb and Robert Rutherford measured a tiny difference in energy levels of the hydrogen atom that classical theory and even early quantum mechanics could not explain. Two energy levels that should have been identical according to the Dirac equation turned out to be slightly different. The explanation, worked out by Hans Bethe and others using quantum electrodynamics, is that the electron in the hydrogen atom is affected by the vacuum fluctuations of the electromagnetic field. The electron interacts not only with the proton it orbits, but also with the vacuum state of the electromagnetic field surrounding it. These interactions shift the energy levels by a small but measurable amount. Again, this is the vacuum, the state with no photons present, affecting the physical properties of a real atom. The vacuum is not passive, it is not inert, it participates in physics. These are not the only examples. The anomalous magnetic moment of the electron, one of the most precisely measured quantities in all of science, also depends on vacuum effects. The electron's magnetic properties are slightly different from what the simplest calculation would predict, and the corrections come entirely from the electron's interactions with the vacuum states of various quantum fields. The agreement between prediction and measurement is staggering, among the most precise in all of physics, and every decimal place of that agreement depends on correctly accounting for what the vacuum is doing. There is also the phenomenon of vacuum birefringence, predicted by quantum electrodynamics, but only recently approached experimentally. In extremely strong magnetic fields, such as those near magnetars, the most intensely magnetic neutron stars, the vacuum itself becomes birefringent. It bends different polarizations of light by different amounts, just as certain crystals do. The vacuum, filled with nothing but quantum fields in their ground state, develops optical properties when placed in a strong enough external field. It behaves like a material, a medium through which light propagates differently depending on conditions. All of this points to the same conclusion. The vacuum is not empty. It is not nothing. It is a real, physical, active state with measurable properties. It responds to boundary conditions. It affects particles. It carries energy. It can be deformed by external fields. It is, in every meaningful sense, a physical thing. So when we ask why quantum fields never stay quiet, we are asking a question about a real physical system, not about an abstraction. The vacuum is not a mathematical convenience or a philosopher's thought experiment. It is the actual physical state of the quantum fields that fill all of space when no particles are present. And the question is, can that state ever be truly, perfectly, completely still? The answer, as the Heisenberg uncertainty principle will show us, is no. And the reason has nothing to do with disturbances from outside, nothing to do with stray particles or imperfect shielding. It has to do with the fundamental mathematical structure of quantum mechanics itself. The laws of physics forbid the fields from being perfectly still. They demand a minimum level of activity, a residual restlessness that can never be eliminated, a hum built into the fabric of reality at the deepest level. The vacuum is the quietest thing that can exist in this universe, but the quietest thing that can exist is not silent. It is a state of minimum noise, not zero noise. And the difference between minimum and zero, a difference that might seem trivial, a difference you might think you could ignore, turns out to have consequences that reach from the tiniest atomic energy levels to the largest structures in the observable universe. To understand why the fields cannot be still, we need to understand one of the deepest principles in all of quantum mechanics. A principle that does not merely limit what we can measure, but limits what can be real. A principle that says certain combinations of physical properties cannot simultaneously have definite values, not because our instruments are crude, but because the universe itself does not assign them definite values at the same time. This is the Heisenberg uncertainty principle, and when you apply it not to a single particle, but to a quantum field filling all of space, something extraordinary follows. The field cannot sit perfectly at a single value. Its amplitude must fluctuate, even in the vacuum, even at absolute zero, even when nothing else is happening anywhere nearby. The field moves because it must, because stillness would require a precision that the laws of quantum mechanics do not allow. Now we arrive at the heart of everything. The reason quantum fields cannot stay quiet, not the description of the fact, but the actual mechanism, the deep physical principle that makes true stillness impossible for any quantum field anywhere in the universe. This is where the story moves from what is happening to why it has to happen. And the answer comes from one of the most profound discoveries in the history of physics. In 1927, Werner Heisenberg was 25 years old. He had already helped create quantum mechanics, developing a mathematical framework called matrix mechanics that could predict the behavior of atoms with unprecedented accuracy. But he was troubled by a conceptual question. In classical physics, you can know everything about a particle simultaneously: its position, its velocity, its energy, its momentum. You can measure all of these at once, with arbitrary precision, and use them to predict exactly where the particle will be at any future time. The universe, in classical physics, is deterministic. If you know the present perfectly, you can predict the future perfectly. Heisenberg discovered that this is not true in quantum mechanics. He showed that certain pairs of physical quantities are linked by a fundamental trade-off. The more precisely you know one, the less precisely you can know the other. This is not a limitation of your measuring instruments. It is not about clumsiness or imprecision in the laboratory. It is a statement about reality itself. These paired quantities do not simultaneously have definite values. The universe does not assign them precise values at the same time. The most famous pair is position and momentum. If you know exactly where a particle is, you cannot know how fast it is moving or in which direction. If you know its momentum precisely, you cannot know where it is. There is a minimum combined uncertainty that can never be reduced below a specific value set by Planck's constant, the fundamental constant of quantum mechanics. This principle is sometimes explained with an analogy about measurement disturbance. The story goes like this. To see where a particle is, you have to bounce a photon off it. The photon disturbs the particle, changing its momentum. So you cannot measure position without disturbing momentum. This analogy has some truth to it, but it gives the wrong impression. It makes the uncertainty principle sound like a practical problem, something you might solve with a more careful measurement technique. It is not. The uncertainty principle is not about measurement disturbance. It is about the fundamental nature of quantum systems. A quantum particle does not have a definite position and a definite momentum simultaneously. It is not that the particle has both, and we just cannot measure them at the same time. The particle genuinely does not possess both properties at once. This is hard to accept, because everything in our daily experience has a definite position and momentum. The chair you are sitting in is in a specific place and is not moving. A car on the highway has a definite position and a definite speed. But at the quantum scale, this is simply not how reality works. Particles exist in states where some properties are inherently indefinite, spread across a range of possible values until a measurement forces one specific value to appear. Now the critical step. The uncertainty principle does not only apply to particles, it applies to fields. And when you apply it to quantum fields, the consequences are extraordinary. A quantum field, as we discussed, has a value at every point in space. At any given location, the field has some amplitude, some strength. It also has a rate of change, how quickly that amplitude is changing at that moment. These two quantities, the field's value and its rate of change at a given point, are related by the uncertainty principle in exactly the same way that a particle's position and momentum are. You cannot simultaneously know both with perfect precision. If the field's value is precisely defined at some point, its rate of change at that point is completely uncertain. If the rate of change is precisely defined, the value is completely uncertain. This has a direct and devastating consequence for the idea of a perfectly still field. What would it mean for a quantum field to be perfectly still? It would mean the field has a definite value at every point, specifically 0, or whatever the equilibrium value is, and that value is not changing. Both the amplitude and the rate of change would be precisely 0, simultaneously, at every location. Perfect stillness requires both the value and its time derivative to be exactly fixed at the same time. But the uncertainty principle says you cannot have both. If the field's value is pinned at exactly 0, its rate of change becomes completely uncertain. It could be changing at any rate. And if the rate of change is pinned at 0, the field's value becomes completely uncertain. It could have any amplitude. You might try a compromise. You might say, fine, I will accept a little uncertainty in both. I will not demand perfect precision in either the value or the rate of change. I will just make both uncertainties as small as possible. The uncertainty principle allows this. It does not say one of the two must be completely unknown. It says the product of the two uncertainties must be at least a certain minimum value. You can spread the uncertainty between the two quantities however you like, but you cannot make both uncertainties 0. This means the field must fluctuate. Not because something is shaking it, not because energy is leaking in from outside, but because the internal logic of quantum mechanics requires it. A field with 0 uncertainty in both its value and its rate of change would violate the uncertainty principle. It cannot exist. Such a state is not merely unlikely, it is physically forbidden. The laws of quantum mechanics do not permit it. The vacuum state, the ground state, the lowest energy configuration of the field, is the state that minimizes the total uncertainty as much as quantum mechanics allows. It is the best compromise between having a well-defined value and a well-defined rate of change. In this state, neither quantity is perfectly defined. Both have a small but non-zero spread of possible values. The field is not sitting at exactly zero, it is hovering around zero, fluctuating slightly, its value jittering unpredictably within a narrow range. These are vacuum fluctuations, and they are a direct, unavoidable, mathematically rigorous consequence of applying the Heisenberg uncertainty principle to quantum fields. Let me make this concrete with numbers, because otherwise it might sound vague. Consider the electromagnetic field in its vacuum state. At every point in space, the electric and magnetic field values are fluctuating. The average value is zero. If you measured the electric field at some point and averaged over many measurements, you would get zero. There is no net field in any direction. But any individual measurement would not give zero. It would give some small, non-zero value, positive or negative, because the field is fluctuating around zero. The fluctuations are real. They are there at every point, at every moment. The size of these fluctuations depends on the scale at which you look. If you probe a large region of space, the fluctuations tend to average out. Positive fluctuations in one area cancel negative fluctuations in another. At large scales, the vacuum looks calm. But if you probe a very small region, the fluctuations become more pronounced. At atomic scales, vacuum fluctuations of the electromagnetic field are significant enough to affect the energy levels of atoms. At subatomic scales, they become even larger. The smaller the region you examine, the more violently the vacuum fluctuates. This is directly related to the uncertainty principle. Confining your observation to a smaller region means you are trying to pin down the field's value more precisely in space, which forces greater uncertainty in other properties, which means larger fluctuations. Now I need to address something important, because at this point in the story, popular science usually takes a wrong turn, and I want to be careful not to follow it. You have almost certainly heard the following description of the quantum vacuum. Empty space is full of virtual particles popping in and out of existence. Particle-antiparticle pairs are constantly appearing from nothing, existing for a brief moment, and then annihilating each other and vanishing again. The vacuum is a seething foam of temporary particles created from borrowed energy that must be paid back almost immediately, according to the uncertainty principle. This description is everywhere. It is in popular physics books, in documentaries, in YouTube videos, in magazine articles. It has become the standard way of explaining vacuum fluctuations to non-physicists, and it is, at best, deeply misleading. Here is the problem. Virtual particles are not real particles that briefly exist and then disappear. They are terms in a mathematical expansion. When physicists calculate the behavior of quantum fields using a technique called perturbation theory, they break complex calculations into simpler pieces. Each piece can be represented by a diagram called a Feynman diagram, which looks like particles being emitted, absorbed, created, and destroyed. The internal lines in these diagrams are called virtual particles. They are computational tools. They represent terms in a mathematical series, not physical events happening in space. This distinction is not a minor technical point, it is fundamental. A real particle has definite properties. It has a specific energy and momentum that satisfy the relationship required by special relativity. You can detect it, you can measure it. A virtual particle does not satisfy that relationship. It cannot be directly detected. It does not exist as an entity in space in the way a real particle does. It appears as part of a calculation, a way of organizing the mathematics of quantum field theory into manageable pieces. The confusion arises because the calculations work. The Feynman diagram approach, using virtual particles as computational tools, gives extraordinarily accurate predictions. The Lamb shift, the anomalous magnetic moment of the electron, the Casimir effect. All of these can be calculated using diagrams that include virtual particles, and the results match experiment beautifully. So it is tempting to say the virtual particles must be real, because the calculations that use them give correct answers. But this reasoning is flawed. The correct answers come from the full calculation, not from any individual diagram. You could reorganize the calculation in a completely different way, without using Feynman diagrams at all, without any concept of virtual particles, and get the same answers. In fact, there are alternative formulations of quantum field theory, such as lattice field theory, where virtual particles never appear. The physics is the same. The predictions are the same. The virtual particles were a useful bookkeeping tool, not a physical reality. So what is actually happening in the vacuum? If it is not particles popping in and out of existence, what is it? The answer is simpler and more honest. The fields are fluctuating. That is it. The quantum fields that fill all of space are in their ground state, and that ground state has non-zero fluctuations because the uncertainty principle demands them. The electromagnetic field at every point is jittering around its average value of 0. The electron field at every point is jittering around its average value. Every quantum field is doing this, everywhere, all the time. These fluctuations are not particles. They are not brief appearances of electrons and positrons, or photons that quickly vanish. They are the irreducible quantum jitter of the fields themselves, a continuous, omnipresent, ineradicable hum of activity in the fabric of the fields. No particles are being created, no particles are being destroyed. The number of particles in the vacuum is exactly 0, and it stays exactly 0. But the fields are not still. They cannot be still, and their restlessness has physical consequences. This is a crucial point that is worth repeating because the particle popping picture is so deeply embedded in popular understanding. The vacuum contains 0 particles, not a fluctuating number that averages to 0, not particles that exist too briefly to count, exactly 0, definitively, at all times. The vacuum state is an eigenstate of the number operator, which is the mathematical object that counts particles. Its eigenvalue is 0. There are no particles in the vacuum, period. But the vacuum is not an eigenstate of the field operator. The field does not have a definite value at each point. It fluctuates. These two facts, 0 particles and fluctuating fields, are perfectly consistent with each other. They are not contradictory. A field can have no excitations, no particles, and still not be sitting at a fixed value. The ground state of a quantum harmonic oscillator has 0 quanta of excitation, but the position of the oscillator is not fixed. It has a probability distribution spread around 0. The oscillator is in its lowest state, but it is still moving. This is exactly what happens with quantum fields in the vacuum. No excitations, but the field values are not fixed. They jitter and fluctuate and refuse to sit still. With this careful understanding in place, let me describe the physical effects that demonstrate vacuum field activity is real and not just a mathematical abstraction. The Casimir effect, which we encountered earlier as evidence that the vacuum has physical properties, takes on new significance in light of what we now understand about fluctuations. Recall that two uncharged metal plates placed close together in a vacuum experience a measurable attractive force because the plates restrict which fluctuation modes the electromagnetic field can support between them. What matters here is what the Casimir effect tells us about the nature of vacuum activity. The force between the plates does not require any particles to exist between them. No photons are being exchanged. No electrons are bouncing back and forth. The particle number between the plates is exactly 0. What produces the force is a change in the pattern of vacuum fluctuations, a reshaping of the field's ground state activity caused by the physical boundary conditions the plates impose. The force is a direct consequence of the fields fluctuating differently in confined space than in open space. This is precisely the distinction we need to hold on to. The vacuum's activity is not particle activity, it is field activity. The Casimir effect does not demonstrate that empty space is full of particles. It demonstrates that the quantum fields filling empty space are in a state of irreducible fluctuation, and that altering the conditions under which those fluctuations occur has measurable physical consequences. Recent experiments using both parallel plate and sphere plate configurations have confirmed the predicted force to within about 1%. The predictions of quantum field theory, based entirely on ground state field fluctuations and zero-point energy, match the measurements with no need to invoke particles appearing or disappearing. The fields fluctuate, the force follows. The Lamb shift reinforces the same conclusion from a different direction. As we saw earlier, the electron in a hydrogen atom is measurably affected by the vacuum fluctuations of the electromagnetic field, shifting energy levels that the Dirac equation predicts should be identical. What is significant here is not just that the effect exists, but that the calculation producing the correct answer treats the vacuum as a fluctuating field, not as a collection of transient particles. The electron is not colliding with short-lived photons materializing nearby. It is immersed in a field whose value at every surrounding point is jittering with irreducible quantum uncertainty. And that jitter slightly smears the electron's effective position, altering its energy in a way that depends on the shape of its orbital. The calculation does not require virtual particles to succeed. It requires a fluctuating vacuum field. This is a crucial distinction. The physically meaningful content of the theory is the field's ground state activity, and the Lamb shift is one of the cleanest experimental confirmations that this activity is real and has measurable consequences for ordinary matter. The Lamb shift was one of the first great triumphs of quantum electrodynamics, and one of the clearest demonstrations that vacuum fluctuations have real physical effects. The electron is not interacting with real photons. There are no photons present. It is interacting with the fluctuating vacuum state of the electromagnetic field, and that interaction changes the measurable properties of the atom. There is another effect that demonstrates vacuum activity with even greater precision: the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet, and the strength of this magnet, called the magnetic moment, can be predicted by quantum electrodynamics. The simplest prediction, from the Dirac equation alone, gives a specific value. But when you include the effects of the electron interacting with the vacuum state of the electromagnetic field, the value shifts slightly. This shift, called the anomalous magnetic moment, or sometimes the G-2 value, has been calculated in quantum electrodynamics to extraordinary precision, including contributions from vacuum fluctuations in the electromagnetic field, the electron-positron field, the muon field, and others. The theoretical prediction and the experimental measurement agree to better than 10 parts per billion. Let me put that precision in perspective. It is equivalent to predicting the length of a 100-meter running track and getting the answer correct to within less than 1,000th of a millimeter. This level of agreement between theory and experiment is unmatched anywhere else in science, and the corrections that make it work, the tiny adjustments that shift the magnetic moment from its simple Dirac value to its measured value, come from the vacuum, from the quantum fields in their ground state interacting with the electron. If the vacuum were truly empty, truly inert, truly nothing, these corrections would not exist. The Dirac equation's simple prediction would be exact. The fact that it is not exact, that there are tiny but precisely calculable and precisely measurable corrections, is direct evidence that the vacuum state of the quantum fields is physically active. Now let me connect all of this back to the zero-point energy we discussed earlier, because zero-point energy and vacuum fluctuations are two faces of the same phenomenon. Remember the quantum harmonic oscillator. Its lowest energy state has energy equal to 1/2 times Planck's constant times the frequency. This energy cannot be removed. It is the minimum that quantum mechanics allows. If you have a collection of oscillators, each one contributes its own zero-point energy. The total zero-point energy is the sum of all the individual contributions. A quantum field can be decomposed into oscillators, one for each possible wavelength and direction of vibration. Each of these oscillators has its own zero-point energy. The vacuum state of the field is the state in which every oscillator is in its ground state, contributing its minimum energy. The total vacuum energy is the sum of all these zero-point contributions. This is the same thing as vacuum fluctuations, seen from a different angle. The zero-point energy of each oscillator is directly related to the fluctuations of that oscillator in its ground state. An oscillator with zero-point energy is one that is fluctuating. It is jiggling with its minimum possible amplitude. The energy and the fluctuations are inseparable. You cannot have one without the other. They are two descriptions of the same physical reality. The Casimir effect can be understood in terms of zero-point energy. The force between the plates comes from the difference in total zero-point energy with and without the plates present. The Lamb shift can be understood in terms of vacuum fluctuations. The energy level shift comes from the electron interacting with the jittering vacuum fields. Both perspectives give the same answer because they are describing the same underlying phenomenon. Let me now address a question that might have been forming in your mind. If the vacuum has energy, if the fields are fluctuating, why do we not notice? Why does empty space not glow or vibrate or feel warm? The answer is that vacuum fluctuations have no preferred direction. They are completely random and isotropic. At any given point, the field is equally likely to fluctuate in any direction, positive or negative, up or down. Over time and space, the fluctuations average to zero. There is no net effect that you would perceive as light or heat or motion. The fluctuations are there, but they are symmetric. They cancel in all directions. They produce no net observable signal in ordinary circumstances. It is only when you change the boundary conditions, when you introduce plates or atoms or curved space-time, when you create an asymmetry in the fluctuations, that measurable effects appear. The Casimir plates create an asymmetry between inside and outside. The hydrogen atom's electron creates an asymmetry because different energy states sample the fluctuations differently. Without such asymmetries, the vacuum fluctuations are real but invisible. They are always happening, but producing no net detectable effect in empty, undisturbed space. This is why it took so long for physicists to recognize the physical reality of vacuum fluctuations. In everyday experience, empty space behaves exactly as you would expect if it were truly empty. Light passes through it, objects move through it. Nothing seems to be happening. The vacuum fluctuations are hidden by their own symmetry. It required extraordinarily precise experiments at atomic and subatomic scales to reveal their presence. There is also an important point about energy. You might wonder if the zero-point energy of the vacuum could be used as a source of energy. After all, if the vacuum has energy, can we not extract it? The answer is no, and the reason is fundamental. Zero-point energy is the minimum energy of the system. You cannot extract it because there is no lower energy state to transition to. It is like asking whether you can extract energy from the ground floor of a building by going to a lower floor. There is no lower floor. The ground state is the bottom. The energy is there, but it is inaccessible. This does not mean vacuum energy has no physical effects. It does, as we have seen. The Casimir effect, the Lamb shift, the anomalous magnetic moment. But these effects involve changing the vacuum energy by altering boundary conditions, not extracting the energy itself. When you bring two Casimir plates closer together, the vacuum energy between them decreases, and that decrease shows up as a force pushing the plates together. The total energy of the system changes, and that change is what produces the measurable effect. But you have not extracted zero-point energy from the vacuum. You have changed the vacuum configuration, and the energy difference between configurations is what does the work. There is one more thing to emphasize before we move on. The vacuum fluctuations we have been discussing are not fluctuations in time in the ordinary sense. When physicists say the vacuum fluctuates, they do not mean the field is calm at one moment and then disturbed at the next, like waves coming and going on a shore. The vacuum state is a stationary state. It does not change over time. It has the same statistical properties at every moment. The fluctuations are built into the state itself. They are not events happening in time. They are a feature of the quantum state, a spread in the possible values of the field that is always present, at every moment, unchanging. This is a subtle point, but it matters. The vacuum is not alternating between quiet and noisy. It is permanently in a state of minimum noise. That minimum noise is always there, always the same, never increasing, never decreasing. It is like the static hiss on an old radio turned to a frequency between stations. The hiss does not come and go. It is always there, built into the system. The vacuum's fluctuations are similar. They are a permanent feature of the ground state, not a dynamic process. So here is where we stand. Quantum fields fill all of space. Their vacuum state, the state with no particles, is not a state of zero activity. It is a state of minimum activity, dictated by the Heisenberg uncertainty principle. The fields must fluctuate because perfect stillness would require simultaneously definite values and rates of change, which quantum mechanics forbids. These fluctuations carry zero-point energy that cannot be extracted. They are not virtual particles popping in and out of existence. They are the irreducible quantum jitter of the fields themselves, and they have been confirmed by multiple independent experiments to extraordinary precision. The quantum fields that fill the universe never stay quiet, because they cannot. Not because something prevents them from settling down, but because the deepest laws of physics, the fundamental mathematical structure of quantum mechanics, make true silence impossible. Quietness, for a quantum field, has a flaw, and that flaw is not zero. It is a specific, calculable, measurable level of residual activity that persists even when every particle has been removed, even at absolute zero, even in the most perfect vacuum that could ever exist. This is not a small technical detail. It is a foundational fact about the universe. The apparently empty space around you, between your atoms, between the stars, in the vast voids between galaxies, is not empty and not inert. It is filled with fields in their ground state, quietly fluctuating, carrying energy, capable of exerting forces and affecting particles. The universe, at its most fundamental level, refuses to be silent. And this refusal, this permanent low hum of quantum field activity, has consequences that reach from the structure of individual atoms to the fate of the cosmos itself. Those consequences are what we turn to next. So now you understand the mechanism. Quantum fields fill all of space. They cannot be removed. Their vacuum state, the quietest configuration they can achieve, is not a state of zero activity, but a state of minimum activity. The Heisenberg uncertainty principle forbids perfect stillness, forcing every field to retain a residual jitter, a baseline of fluctuation that persists even when no particles are present. This is not speculation. It is confirmed by the Casimir effect, the Lamb shift, and the anomalous magnetic moment of the electron. Experiments that match theoretical predictions with extraordinary precision. But understanding that the vacuum is restless is only the beginning. Because once you accept that empty space carries energy, once you accept that the vacuum state of every quantum field has real physical content, you run straight into some of the deepest unsolved problems in all of physics. Problems so severe that they expose cracks in our understanding of reality itself. And you also discover that the restless vacuum connects to phenomena far stranger than anything we have discussed so far. Phenomena that link the quantum behavior of fields to the warping of space-time, the evaporation of black holes, and the ultimate fate of the universe. Let us start with the most famous problem, the cosmological constant problem. It has been called the worst prediction in the history of physics, and that description, if anything, understates it. Here is the issue. We know the vacuum has energy. Every quantum field contributes zero-point energy from its ground state fluctuations. If you try to calculate the total vacuum energy by adding up the contributions from all known quantum fields at all possible wavelengths, you get a number. And that number is enormous. How enormous depends on where you cut off the calculation. Quantum field theory works beautifully up to certain energy scales, but we know it must break down at some point, probably around the Planck scale, where quantum gravity effects become important. If you sum up the zero-point contributions from all field modes up to the Planck energy, you get a vacuum energy density of roughly 10 to the power of 113 joules per cubic meter. That is an incomprehensibly large number. Every cubic meter of empty space, according to this naive calculation, should contain more energy than all the stars in the observable universe combined. Now, Einstein's general theory of relativity tells us that energy curves spacetime. All energy, including vacuum energy. If the vacuum has energy, that energy should gravitate. It should curve space. It should affect the expansion rate of the universe. In Einstein's equations, vacuum energy appears as something called the cosmological constant, a term that describes a uniform energy density filling all of space and driving either the acceleration or deceleration of cosmic expansion. So we can check. We can look at the actual universe and measure how fast it is expanding and whether that expansion is accelerating or decelerating. In 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is accelerating. Something is pushing space apart, causing galaxies to recede from each other faster and faster over time. This something behaves exactly like a cosmological constant, a uniform energy density filling all of space. The measured value of this dark energy, as it came to be called, corresponds to a vacuum energy density of roughly 10 to the power of -9 joules per cubic meter. That is extraordinarily small. It is so small that its effects are only noticeable on the largest cosmological scales, across distances of billions of light years. Now compare the two numbers. The theoretical prediction from quantum field theory is roughly 10 to the 113 joules per cubic meter. The observed value is roughly 10 to the -9 joules per cubic meter. These numbers differ by a factor of roughly 10 to the 122. That is a 1 followed by 122 zeros. It is the largest discrepancy between theory and observation in the entire history of science. Nothing else even comes close. Let me try to convey how absurd this discrepancy is. If you were trying to predict the weight of a cat, and your calculation gave you a number larger than the mass of the observable universe, you would know something was deeply wrong with your calculation. The cosmological constant problem is worse than that. It is not a factor of 10 or 100 or even a billion off. It is 10 to the 122 off. The prediction overshoots the observation by more orders of magnitude than you could reasonably write down on a piece of paper. This is not a problem with sloppy physics. The calculations are done correctly using the standard tools of quantum field theory, the same tools that give spectacularly accurate predictions for everything else. The Lamb shift, the anomalous magnetic moment, the Casimir effect, all are calculated using the same framework and all agree with experiment to extraordinary precision. The theoretical machinery works. It just gives a catastrophically wrong answer for the total vacuum energy. Several possible resolutions have been proposed, but none is fully satisfactory. One possibility is that something cancels the vacuum energy almost perfectly. Perhaps different fields contribute positive and negative zero-point energies that nearly cancel each other out, leaving only the tiny residual we observe. Supersymmetry, a theoretical framework proposing that every known particle has a heavier partner particle, would provide exactly this kind of cancellation. In a perfectly supersymmetric universe, the vacuum energies of particles and their partners would cancel exactly, giving zero total vacuum energy. But supersymmetry, if it exists, is clearly broken in our universe. The partner particles have not been found at the energies probed by the Large Hadron Collider. If supersymmetry is broken, the cancellation is imperfect, and you are left needing to explain why the remaining vacuum energy is so incredibly small, but not zero. The cancellation would need to be perfect to 122 decimal places, and then fail at the 123rd. There is no known mechanism that could produce such exquisite fine-tuning. Another possibility is that we are calculating the vacuum energy wrong. Perhaps our method of summing zero-point contributions is naive, and a more sophisticated treatment would give a smaller answer. This is plausible. We do not have a complete theory of quantum gravity, and vacuum energy involves the intersection of quantum mechanics and gravity, exactly the regime where our current theories break down. Perhaps a correct theory of quantum gravity would naturally produce a small cosmological constant. But we do not have such a theory, so this remains a hope rather than an explanation. A third possibility involves the anthropic principle. If the universe is part of a vast multiverse, where different regions have different values of the cosmological constant, then we necessarily find ourselves in a region where the constant is small enough to allow galaxies, stars, planets, and observers to exist. If the cosmological constant were much larger, The universe would expand too rapidly for matter to clump together. No galaxies would form, no stars, no planets, no life. No one would be around to measure the cosmological constant, so the fact that we measure a small value might not require a physical explanation. It might just be a selection effect. We exist where we can exist. This reasoning is controversial. Many physicists find it unsatisfying because it does not explain anything in the usual scientific sense. It does not identify a mechanism or make a unique prediction. It simply says the value is what it is, because if it were different, we would not be here to notice. Whether this counts as an explanation or an abdication of explanation is a matter of ongoing debate. The cosmological constant problem remains one of the great unsolved mysteries of modern physics. It tells us something important. We understand vacuum fluctuations well enough to calculate their effects on atoms with astonishing precision. But we do not understand how to correctly calculate their gravitational effects on the universe as a whole. Something fundamental is missing from our understanding. The vacuum energy is real, its local effects are confirmed, but its behavior on cosmological scales remains a deep puzzle. Now let us turn to another remarkable consequence of the restless vacuum, one that connects quantum field fluctuations to one of the most exotic objects in the universe: black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. It forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. If the star is massive enough, no known force can halt the collapse. The matter compresses to extraordinary density, and the gravitational field becomes so strong that it warps space-time into a one-way boundary called the event horizon. Anything crossing the event horizon, matter, light, information, falls in and cannot return. For decades, black holes were thought to be perfectly black. They absorbed everything and emitted nothing. They were the ultimate endpoints, cosmic drains from which nothing could escape. This picture seemed airtight. The event horizon was an absolute boundary. Once inside, you were gone. Then in 1974, Stephen Hawking discovered something extraordinary. By applying quantum field theory to the curved space-time near a black hole's event horizon, he showed that black holes are not perfectly black. They emit radiation. They glow. And they do so because of the quantum vacuum. Hawking's calculation is subtle and often misrepresented in popular accounts, so let me describe it carefully. The standard pop science explanation goes like this. Near the event horizon, virtual particle pairs pop into existence. One particle falls into the black hole while the other escapes. The escaping particle becomes real radiation, and the infalling particle has negative energy, reducing the black hole's mass. This description uses the virtual particle language we already identified as misleading. It gives a picture that is vivid but physically inaccurate. What Hawking actually showed is more interesting and more honest. He showed that the concept of a particle, the concept of what it means for a field to be in its vacuum state, depends on the observer. This is one of the most profound and unsettling results in all of theoretical physics. In flat space-time, far from any gravitational field, there is a well-defined vacuum state. All observers agree on what the vacuum is. They all agree on the particle count. If one observer says there are 0 particles, all observers agree. But in curved space-time, near a black hole, this is no longer true. The vacuum state as defined by an observer falling into the black hole is different from the vacuum state as defined by an observer far away from the black hole. What one observer calls empty, the other calls full of particles. This is worth pausing on because it overturns something you might have assumed was beyond dispute. You probably thought the question, "Are there particles here or not?" has a single, definite answer. Either there is an electron at this location, or there is not. Either this region contains photons, or it does not. In flat space-time, far from strong gravitational fields, that assumption holds. All observers agree on the particle count. The vacuum is the vacuum for everyone. But general relativity tells us that space-time is not flat everywhere. Mass and energy curve it. Near a black hole, space-time is severely curved, and the curvature is not uniform. It changes dramatically from one region to another. An observer freely falling through the event horizon experiences space-time differently from an observer hovering at a safe distance. Their clocks tick at different rates, their rulers measure different lengths, and crucially, their definitions of what counts as a positive frequency field oscillation, the definition that determines what a particle is, differ. The falling observer defines particles one way, the distant observer defines them another way. Neither definition is wrong. They are both valid in their respective reference frames, but they disagree about whether particles are present. The vacuum, the supposedly empty state, is not an absolute concept. It is relative. It depends on the observer's state of motion and the geometry of the space-time they inhabit. Specifically, Hawking showed that if you start with a quantum field in the vacuum state, as defined by an observer far from the black hole, the natural state for fields in flat space-time, then near the event horizon, the gravitational field of the black hole distorts this state. The curvature of space-time mixes what the distant observer would call positive and negative frequency field modes. Modes that the distant observer interprets as particles get entangled with modes that fall behind the horizon. The result, as seen by the distant observer, is a steady stream of particles radiating away from the black hole. This radiation has a thermal spectrum, meaning it looks like the glow of a hot object. The temperature of this radiation is inversely proportional to the black hole's mass. Large black holes have very low temperatures. A black hole with the mass of the Sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background, and utterly undetectable with current technology. But smaller black holes would be hotter. A black hole with the mass of a mountain would glow with a temperature of billions of degrees, emitting a torrent of high-energy radiation. The crucial point is this: Hawking radiation is not caused by particles popping out of the black hole. Nothing escapes from inside the event horizon. The radiation comes from the quantum fields outside the horizon, fields that fill all of space, fields in their vacuum state. The gravitational field of the black hole curves space-time in a way that changes what the vacuum state looks like. It transforms the quantum fluctuations of the vacuum into real, detectable particles for a distant observer. The restless vacuum, the same vacuum whose fluctuations produce the Casimir effect and the Lamb shift, is responsible for Hawking radiation. The fields cannot be quiet. Their ground state activity, combined with the curvature of space-time near a black hole, produces real particles. The black hole does not create the radiation, the vacuum does. In the presence of extreme space-time curvature, the black hole's gravity acts as a catalyst, converting vacuum field activity into observable particles. Hawking radiation has profound implications. It means black holes are not eternal. They lose energy through radiation. As they radiate, they lose mass. As they lose mass, they get smaller. As they get smaller, they get hotter, radiating more intensely. The process accelerates. Eventually, the black hole evaporates entirely, vanishing in a final burst of radiation. For a black hole with the mass of the Sun, this process would take roughly 10 to the 67 years, incomprehensibly longer than the current age of the universe. But for smaller black holes, it would happen faster, and in principle, every black hole in the universe will eventually evaporate, converted entirely into radiation by the restless quantum vacuum. This raises the black hole information paradox, one of the deepest unsolved problems in theoretical physics. If a black hole forms from the collapse of a star, all the information about that star, its composition, its structure, the quantum states of all its particles, falls behind the event horizon. When the black hole evaporates via Hawking radiation, what happens to that information? Hawking's original calculations suggested the radiation is perfectly thermal, meaning it carries no information about what fell in. If that is correct, then when the black hole evaporates completely, the information is gone, destroyed. But quantum mechanics says information cannot be destroyed. The evolution of quantum states is unitary, meaning it preserves information. Burning a book does not destroy the information in it. In principle, if you could track every particle of smoke and ash, you could reconstruct the book. Quantum mechanics guarantees this. But black hole evaporation appears to violate this guarantee. Information goes in and does not come back out. This paradox has driven decades of research. Many physicists believe the information must somehow be encoded in the Hawking radiation, carried out in subtle correlations between the emitted particles that Hawking's original calculation did not capture. Recent theoretical work, involving concepts like the holographic principle and quantum entanglement entropy, suggests this might be the case. But the full resolution remains unclear. The paradox sits at the intersection of quantum mechanics and general relativity, exactly where our current theories conflict, exactly where a theory of quantum gravity is needed. And all of it traces back to the simple fact that quantum fields never stay quiet. The vacuum fluctuations that cause the Casimir effect, that shift the energy levels of hydrogen, that correct the electron's magnetic moment, are the same fluctuations that, in the presence of extreme space-time curvature, produce Hawking radiation and lead to one of the most profound paradoxes in physics. There is another cosmological connection worth exploring. In the very early universe, fractions of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, space expanded exponentially, doubling in size roughly every 10 to the negative 37 seconds. In a tiny fraction of a second, a region smaller than an atom was stretched to a size far larger than the currently observable universe. Why does inflation connect to vacuum fluctuations? Because the seeds of all the structure we see in the universe today, every galaxy, every cluster of galaxies, every void between clusters, originated as quantum fluctuations during the inflationary epoch. The quantum fields present during inflation were fluctuating in their vacuum state, jittering with the irreducible randomness that the uncertainty principle demands. Inflation took these microscopic quantum fluctuations and stretched them to macroscopic scales. Fluctuations that started at subatomic sizes were expanded to sizes spanning millions of light years. After inflation ended, these stretched fluctuations became tiny variations in the density of matter and radiation, frozen into the fabric of the expanding universe like a pattern pressed into cooling glass. The variations were extraordinarily small, roughly 1 part in 100,000, barely distinguishable from perfect uniformity. But they were there, imprinted across the entire observable universe, each one tracing its origin to a quantum fluctuation that had been microscopic a fraction of a second earlier. And those variations, subtle as they were, would eventually determine the structure of everything we see in the night sky. The Planck satellite measured these temperature variations to a precision of a few millionths of a degree. The resulting map is speckled with regions slightly warmer and slightly cooler than the average, each warm spot corresponding to a region that was fractionally denser in the early universe, each cool spot corresponding to a region fractionally less dense. Those differences were astonishingly small, but gravity is patient. Over hundreds of millions of years, the slightly denser regions pulled in surrounding matter, growing incrementally heavier, attracting still more material, collapsing slowly inward under their own weight, until they became the dense knots of gas that ignited as the first stars and assembled into the first galaxies. The voids grew emptier as matter drained away toward the dense regions. Filaments of galaxies formed along the boundaries between voids, creating the vast cosmic web that large-scale surveys have mapped across billions of light-years. Every strand of that web, every cluster and supercluster of galaxies strung along it, traces its ancestry to a quantum fluctuation smaller than an atom, stretched to cosmic proportions by inflation, and then sculpted by gravity over billions of years. The match between the predictions of inflation, based on quantum vacuum fluctuations, and the observed pattern in the cosmic microwave background is remarkable. The fluctuations have the right statistical properties, the right distribution of sizes, the right relationship between large-scale and small-scale variations. The structure of the entire observable universe, the arrangement of hundreds of billions of galaxies across 93 billion light-years of space, traces back to the quantum jitter of fields in their vacuum state during the first moments of cosmic history. This is perhaps the most dramatic demonstration of the physical reality of vacuum fluctuations. They are not abstract theoretical constructs. They are not mathematical artifacts. They are the origin of everything you can see when you look up at the night sky. Every galaxy, every star, every planet exists because quantum fields could not stay quiet during the first instance of the universe. The structure of the cosmos is a magnified image of vacuum fluctuations, written across the sky in the distribution of matter and light. Let us step back now and consider what all of this means for how we understand reality. The picture that emerges from modern physics is very different from the one most people carry in their heads. In the common picture, the universe is a collection of objects, particles, atoms, planets, stars, sitting in empty space. Space is the container, matter is the content. Between the objects there is nothing, emptiness, void. The real picture is radically different. There are no objects in the fundamental sense. There are fields, quantum fields that fill all of space, overlapping, coexisting, extending without boundary. What we call particles are localized excitations of these fields, temporary ripples that come and go. What we call empty space is the vacuum state of these fields, a physically real state with real energy and real activity. There is no container separate from the contents. The fields are the physical reality at every point, and even in their quietest state, they hum with irreducible activity. The universe is not a box containing things. It is a web of fields whose excitations we perceive as things, and the web never stops vibrating. It cannot stop. The laws of quantum mechanics, specifically the uncertainty principle, forbid it from ever achieving perfect stillness. The vacuum, the emptiest possible state, is not empty. It is the lowest hum the universe can produce, and that hum is always there, at every point, at every moment. This reshapes how we think about some of the most basic concepts in physics. Take the concept of nothing. In everyday language, nothing means the absence of everything. But in physics, there is no such state. You cannot have a region of space with no fields. The fields are not optional features of space. They are part of what space is. Even if you could somehow remove the fields, which you cannot, you would also remove space itself, because the geometrical properties of space are described by yet another field, the gravitational field, or the metric field in Einstein's general relativity. Remove all the fields, and you have removed space and time as well. You do not have an empty container. You have no container. You have nothing in the deepest sense. A state that may not even be physically meaningful. So when physicists say the vacuum is not nothing, they are making a precise and profound statement. The vacuum is a state of minimum excitation, not a state of non-existence. And the difference between minimum and zero, between the quietest possible hum and absolute silence, is the difference between a universe that has structure and physical content and a state of non-existence that may not even be coherently describable. This understanding also reshapes how we think about energy. In classical physics, a system's energy can be zero. A particle sitting still at the bottom of a potential well has zero kinetic energy, and by convention, zero potential energy. It is doing nothing. It has nothing. But in quantum physics, no system can have zero energy. Every system, from a single oscillator to a quantum field filling the universe, has a non-zero ground state energy. This zero-point energy is the price of existence in a quantum universe. It is the minimum cost the uncertainty principle charges for the field to exist at all. You can have a field with no excitations, no particles, nothing happening. But you cannot have a field with no energy. The act of existing, of being defined at every point in space with a value and a rate of change that cannot both be precisely fixed, carries an irreducible energy cost. The universe pays this cost everywhere, at every point, for every field. The total energy is the sum of contributions from every field at every location, an enormous quantity that, as we discussed, leads to the cosmological constant problem. We do not know how to correctly account for this energy in the context of gravity and cosmology, but its local effects are real, measured, and understood with extraordinary precision. There is something humbling about all of this. We live our lives surrounded by what appears to be empty space. The air in a room seems like nothing between you and the far wall. The vacuum of outer space seems like the ultimate emptiness. But every point you can see or point to, every location in the universe, is filled with quantum fields in their ground state, quietly fluctuating, carrying energy, participating in the physical processes that shape reality. The space between your hand and this screen is not empty. It is alive with the irreducible activity of quantum fields that have been present since the universe began and will remain present as long as space-time exists. The vacuum is not silence. It is the quietest possible sound the universe can make. And from that quiet, from those irreducible fluctuations, everything emerged. The density variations that became galaxies, the energy shifts that determine how atoms behave, the radiation that slowly dismantles black holes over timescales longer than the current age of the cosmos, the mysterious dark energy that is pushing the universe apart, accelerating its expansion into an uncertain future. Quantum fields never stay quiet because the universe does not permit them to. Stillness is not an option the laws of physics offer. The uncertainty principle, the most fundamental constraint quantum mechanics imposes, ensures that every field at every point retains a minimum tremor that can never be silenced. This tremor is not a flaw. It is not noise to be eliminated. It is a feature of reality at its deepest level. Without it, atoms would not have quite the properties they have. Without it, the large-scale structure of the cosmos would not exist. Without it, black holes would be truly black, truly eternal, truly featureless. The restless vacuum is not a complication layered on top of a simpler, quieter reality. It is the ground floor. It is where physics begins. The next time you look at what appears to be empty space, between the stars on a clear night, in the gap between objects on a table, in the pause between one thought and the next, remember what is there. Not nothing, not void, not silence, but the quietest hum the universe is capable of producing. A hum carried by fields that have been present since the first moments of time. A hum that gave rise to every structure in the observable cosmos. A hum that can never be switched off, because the laws of physics themselves keep it going. The universe, at its most fundamental level, is incapable of being perfectly still. And that inability, that restlessness woven into the very fabric of quantum fields, is one of the most profound and beautiful facts about the reality we inhabit. Thank you for joining me on this journey into the heart of what empty space actually is. If you found this exploration valuable, a like or subscribe goes a long way in helping this channel continue making these deep dives into the most fascinating questions in physics. The universe is never quiet, and now you understand why. Sleep well tonight, knowing that even in the stillness of your room, in the darkness and the silence, the quantum fields filling every point around you are humming with activity that has persisted since the beginning of time and will continue long after the last star has gone dark. The vacuum is not empty, the silence is not silent, and the nothing you thought was there has been something all along.